early in the morning before 8. I'm never gonna get these things. I just ordered one on Amazon and it'll get here when it gets here.
Koozie.
Wait. Yeah, it is. Hector's here. It's a little rubbery. But he's there. I don't know. Came with the keys when I ordered it.
I have to I was that one.
Oh, was it?
Yeah, let's see which key.
Yeah, he's all worn out and it's very used to.
Yeah, all right.
Yeah, that's what year is it?
Early 2015.
Okay.
Yeah, that's your head over. You're gonna be.
The Ultimate One, we can actually upgrade the hard drive on it.
Oh, okay.
So I don't think I'm gonna upgrade it.
Yeah.
Sticking 2 terabytes in there, and then it's probably good for the rest of my life.
Right.
Hi Noel, sorry I ignored you earlier, but I see your message. We'll talk. I know you can hear me.
You're good, thank you.
Was that from them?
Yeah, that was Noel.
Right. Because on data mining, the volume is so low. Where do you control the volume?
I don't think it was coming out the right speakers earlier today.
Yeah.
Yeah, it's coming out of the last desktop in there, right? Yeah.
You can see that here the configuration is different.
Yeah. But I have another class in there and it worked.
Yeah, it worked.
It worked like the other day, yesterday. It works for Algo, right? And
Yeah, it works
So
Algo,
the
yeah.
problem is me.
Yeah. I don't think it's the room.
Or the instructor who was here before you, potentially. I like that.
Yeah, I like that idea.
All of you guys at the same time. It's like awesome.
Yeah. I told you, he's hearing everything. They can hear me right now. You guys hear me?
What? Today we're going to talk about the syntax analyzer or parser. Talk about types of parsers. We're going to focus on the top-down parser. A specific top-down parser called the recursive descent parser. So at this point, you understand the initial phase of the compilation process, which is the scanner or the lexicon analyzer, which basically, what is this flick?
Back connection.
I'm blinking on that though.
So this process, as we discussed, it reads the source file. We evaluate it, right? Read one character at a time. And as it reads the source file, it'll try, the lexicon analyzer will try to identify words with some syntax meaning, such as identifiers, keywords, symbols like arithmetic operators, brackets like delimiters, like braces, brackets, parentheses, all those symbols, they need to be identified and they are classified with the token value. So basically, this is the role of the lexicon analyzer. We discussed an implementation from scratch of a lexicon analyzer in Scala, right? And we also discussed that there are tools that enable the creation of lexicon analyzer from a set of specifications. We discussed one tool, which is called JFlex, and it's based on Flex. Flex generates lexicon analyzers in C, and before that, before Flex, there was the Lex. So Flex is the faster version of Lex, or the newer version of Lex. So let's move on this process and discuss the second phase of the compilation process, which is the syntax analyzer, or normally called just the parser. The syntax analyzer will understands the grammar of the language. So it fully understands the syntax of the language. If I have in my source code something like equal, I don't know, 5, and then X, then a semicolon, the lexicon analyzer understands that this is an assignment operator. Understand that this is a literal value. This is an identifier. This is a semicolon. So for the lexicon analyzer, this looks fine, right? But for the syntax analyzer, these tokens, right? They are out of order, right? The syntax analyzer should expect something like a typical assignment, right? And the syntax that describes that an assignment statement has to be written in this particular order. This is described in the grammar of the language, right? So in the grammar of the language, you will have something like maybe a production rule that says a statement, right? A statement can be an arrow. This can be an assignment statement, right? Or some other statement. An assignment statement is defined as an identifier, right? Typically, in an assignment, this is called the L value. So the L value has to be an identifier, and then you have this token representing the assignment operator, and then usually you have an expression, right? An expression and a semicolon. So this is one possible expression. So later you will have to specify the grammar. The grammar will specify what is an expression, what is this R value of an assignment statement. An expression can be many things, right? It can be addition of two expressions, comparison of two expressions, and can also be, at the end, it can be a factor, right? And this is a factor, it's just a literal value, right? It can be a literal value, it can be another variable. So at this point, hopefully you guys understand that the lexicon analyzer has a limited scope, right? The scope of the lexicon analyzer is just to identify the tokens, but it doesn't know about the grammar of the language. So that's the job of the syntax analyzer. So the syntax analyzer will use the productions of the language, grammar, to verify if the code is syntactically correct. One of the outputs of the syntax analyzer is the parse tree. So the parse tree describes the hierarchical structure of a program as defined by the programming language grammar. What's on the root of this parse tree? The root of the parse tree, remember?
Is it a symbol table?
Yeah. The start symbol, right? The start symbol. The start symbol is the root. And then as we go down, right, on the sparse tree, you're going to have inner nodes, variables, and leaf nodes, they will be terminals, right? So the parse tree has the start symbol as its root, variables as internal nodes, and terminals as leaf nodes. Terminals are not just a single terminal, a combination of terminals to form a word of your language, right? So this, this is a very simple grammar that is only able to describe expressions, arithmetic expressions. So this is how it looks like. You have an E of an expression. It's an expression plus a term. This expression on the left side is a multiplication, so it goes to a term. A term is a multiplication of a term and a digit. The digit is the digit 5. So you can see our goal, the goal of the syntax analyzer is to be able to build the sparse tree, because this sparse tree represents your code, a code that is syntactically correct, okay? So there are basically two approaches for building a syntax analyzer. You can, and those approaches, they differ based on how you're going to build the parse tree. Okay, so you can have a top-down approach. So you build the parse tree top-down, or a bottom-up approach. The bottom-up, you use a combine the elements as you identify in the source code into the variables until eventually you reach the start symbol. The top-down approach, you start this with the start symbol, assume start symbol, and then you choose the right production that will lead to the parse tree to be built. So you do top-down. Okay, so let's talk about the top-down parser. So the process begins with the grammar start symbol, the root of the parser. At each iteration of the process, the parser tries to determine or predict which production to apply in order to get closer to the word to be generated. This process is sometimes not trivial because, as you know, some productions will have the or, right? So you don't have just one choice. If we had just one choice, it's pretty easy, right, to go top down. But sometimes you have more than one choice. So which production should you choose? So if you have a situation where this is the start symbol, and then you can go A, B, or C, right? How are you going to choose which one to pick, right? Should we pick A, B, or C? So it's hard sometimes to decide. So consider a scenario where the current derivation is x, a, and some alpha. So that's what we have at this point. So x is a terminal. So everything that is lowercase, you assume it's a terminal or a combination of terminals. And whatever is uppercase, consider it's a variable. Alpha is what we still need to evaluate. So alpha is like the input, okay? So we evaluated up to this point. So we were able to identify x. X can be more than one word, so that part is resolved. And right now we have a variable a that we want to descend, and we have the input containing something that we're just calling it alpha. And of course, you need to figure out what you should do with A, right? So consider that there are these three options here. You can have A going to little a, or you can go to B, little b, and some B variable, or you can do the CBC. Okay, so how can a top-down parser decides? How can it decide which rule to apply? Okay, so you have the scenario here, and how can you figure out which rule to apply? So what do you guys think? Just by looking at these productions, what should we do? What will be your, if you were a syntax analyzer, how would you decide? Alpha is the inputs. You can look at the character that is coming from the input, not the character, the token, right? We're talking about token. So you can look at the token that is coming. Based on the token, can you figure out where to go? Right? So if the token that is coming matches little a, that's obvious, right? You should consume that token, right? And apply a going to alpha, to little a. Or if it's coming a b, you should do the second one, or a c, you go to the third. So that decision was easy, right? So if the next token is an a, apply a, go to little a. If it's b, go to b. And if c, you do the other one. That only worked because all three rules were recursive productions. What does it mean? Well, you figure out where to go because you were able to look at the productions, and the first symbol on the right-hand side of the productions were the symbol was a token. So that was easy, right? But what if it wasn't a token? What if it was a variable, right? So that's a problem that we have to face when, and we need to figure out what to do if our grammar has left recursive productions. So that's a restriction. For a top-down parser, and specifically this recursive descent parser, it only works if the productions are right recursive, or they don't have recursion at all. But if they are left recursive, the parser becomes much more complex and difficult to implement, okay? So, all right, so that's a limitation, but it's not a big limitation because it's just a matter of transforming, working on, with your grammar and make sure you eliminate all the left recursive productions and make them right recursive productions. And we know how to do that, right? Actually, I'm going to give you an algorithm that removes left recursive productions. So if you have these, this is the algorithm. If you have recursive productions like this, so left recursive production, so why this is a left recursive production? The A symbol, right, on the left-hand side appears on the left side of the right-hand side of the production. So the A's appear on the left side. All of the A's appear on the left side. You want to eliminate those. The rule says you replace all these rules here. You have to replace them using those productions here. Those beta 1, or to beta n, they don't have A on the left side, okay? So you're gonna use those, and you're gonna replace these, A going to A alpha 1 and until A going to A alpha n. You're going to replace those by beta 1 alpha prime. So you're gonna create another variable until beta n alpha prime. And then what is alpha prime? Alpha prime is alpha 1, those alpha 1s here, and A prime. So you basically you replaced left recursive productions with right recursive production. And don't forget the epsilon. So this algorithm works. Let me show you an example. Try to replace the left recursive productions here. Okay, so let's apply the algorithm. So what we have here is just one left recursive production. And this is going to make our parser too complex. So let's eliminate this left recursive production. And this is what we have. So this guy here, using the algorithm, this is the A, okay? And this part here is the alpha, all right? This guy here is the beta. So the algorithm is saying that you have to do T, right, which is beta, and use another symbol, E prime, okay? And then you do E prime, and you will do that if you had other betas, other terms that weren't left recursive, you will do for each of them, okay? But we only have one here. And now E prime, I'm going to do what? Alpha plus T, E prime, right? So right recursive now, and then I'll do epsilon, okay? So this is the process to remove productions that are left recursive. The question is, are these similar? Are they producing the same thing? So let's take a look here. This left recursion here is basically saying that I can replace E with E plus T. So basically I can do T plus T plus T, right? Many times. Eventually I will turn this E, right, into a T, right? Basically this is what we can get, right? Or we can generate using these productions. I can do many E plus T, E plus T. When I'm tired, I turn the left E into a T. So I have a sequence of T plus T, right? Can I do the same here? So here is saying that you should do T, right? And then E prime. This E prime, you're gonna turn into many plus T E prime. Turn the E prime into plus T, right? E prime. So you can do many of those. Eventually, when you're tired, you turn that E prime into epsilon. So you end up with the same thing, a bunch of T plus T's. Okay? So do you agree that these are similar? This algorithm works, okay? This was a theory of computation class. We would come up with a proof that the algorithm works for any case. This is more, we're not doing that, right? So ask Dr. Paul, but intuitively we can see that this works, right? So how about, this is showing the result, right? Before we do that, I think we should practice. Let me see if I have an activity for you guys to do. I didn't update that, so let me do that really quick. I have thought I had, oh, it's actually a quiz. Okay, so let me give you one here. Another one for you guys to try. Just a simple exercise, very similar. Apply the algorithm to remove this here. So factor, right? So factor goes to, no, actually term. Term goes to term times vector, or term divided by factor, or vector. Okay? So remove the left recursion of these production strands. Then when you're done, do this other one here.
Oh, yeah, that's right.
This is actually more complex than what I'm trying to convince you to think. Because sometimes the recursion is indirect, okay? So when you have indirect left recursion, that's harder to do. But you can make a program that does that. But it's more manual work. You have to eliminate all of that. But that's more theory of computation. To understand more the language, the grammars we're going to use, they're going to be much more simple.
Yeah, it's not T prime.
All right.
T goes to T prime. T prime. I need a. It's awful. Juice over there. With juice.
Jesus. What do I got?
But do you have to even? I mean, you could take care of it. Yeah,
So
it's
what
just-
empties just want to recurs, right, no matter what it is.
Yep.
Right.
Yeah.
Okay, so
No,
you guys
T can't go.
got it? Easy? All right, so you have to do T going to, right, F, right? T prime. right? And then t prime going to multiplication f t prime or division f t prime or epsilon. Okay? So if you want to just go t to factor straight, you just need to do t f t prime and then t prime epsilon. But if you want to do, for example, t times t divided by t, for example. So using the new productions, you do f t prime. Then you turn this t prime into multiplication, right? Multiplication f, right? T prime. Okay, and then you turn this one now into division f t prime. Right, so you have all that you want. You just need to turn t prime into epsilon. Good. All right. So if you were to do using the original productions, you would do this one, and then you turn. Actually, you would do because it's left recursive. You would need to apply this one first, right? It's kind of counterintuitive, right? Because usually you like to evaluate from left to right, but you will do it differently, right? Do we have lefties here? So the lefty ones probably prefers this one. My daughter, she's a lefty. So T going to Dave. My parents said that I was supposed to be a lefty, but the teachers, they kind of forced me, and that's why my handwriting is so bad.
Let's go with that now, yeah.
You can see that, right? So you would do t divided by f, and then t times f, and then you turn that last t to an f, right? That left side t to an f. Okay, now how about this one? Right? So you do x. Help me out here.
X goes to CX prime,
Cx prime.
and X prime goes to AX prime or BX prime or epsilon.
Awesome. Okay. Hard to read, right?
Yeah, that's not X. That's
All right, so x go to cx prime, and then x prime go to ax prime or bx prime or epsilon. Awesome. Okay. So now let's think about. So that's the first step, right? Before you actually start thinking about writing the parser, if you're using the recursive descent parser, the top-down approach, the first step is to remove left recursions, substitute them with right recursion, okay? So the recursive descent parsing process is a top-down parsing implementation. It consists of a collection of subprograms. Subprograms can be a function, can be a method, right? And if you're using object-oriented programming, but just a subprogram, just a code. And these subprograms, they're possibly recursive because if you are coding, for example, t prime, right, going to multiplication ft prime. So this is what you're evaluating in your procedure. At some point, right, because you're seeing a t prime, this is a call to the function that evaluates this production, right? So that's a recursive call. That at the end generates a parse tree in top-down fashion. So recursive descent parser generally has a subprogram, so it's easy to code because for each production, you're gonna have a subprogram. Okay, so this is gonna be a subprogram. This is gonna be actually you can actually code all of these in just one function, right? Because those are very similar. So you can do, so basically for each variable, right, basically you're gonna have one function. So that's what it's saying here. You're gonna have a subprogram for each non-terminal in its associated grammar, for each variable. So now let's look at our implementation. The syntax analyzer class will have a parse method that returns the parse tree. Okay, so the parse method is the main method we'll be working at. Of course, this parse method starts by calling the procedure that will evaluate the start symbol, right? And use that top down. Important methods are in this implementation that we're going to talk about are the get lexeme and next lexeme. So remember the syntax, the lexicon analyzer had get char and next char. You guys remember that, right? You did the homework, right? The get char, so they're very similar here, but instead they are reading lexeme and token, or lexeme objects. The lexeme object has the symbol, right? That was evaluated in the token value, right? So, and they work similarly in the sense that you can call get char as many times as you want. It will always return the character that is being read from the input, right? Always the same character, because get char does not consume the input, right? So you call get char, and if you're ready to move forward, you have to call next char to say, look, I want to move forward the input one character. The same here, get lexeme and next lexeme. So get lexeme will ask the lexicon analyzer for the for lexeme, right? But you can call get lexeme many times, and it will always return the same. In order to move forward for the actual next token, you have to call next lexeme to advance the flow. Okay, this is important because sometimes during the implementation of one of these productions, you will read the input, but you decide that the input is not, it's like, oh, this input is basically telling me that I'm done and I need to pass the control for another function, right? Because this lexeme is part of another production. So I just need to finish my procedure and let another procedure to continue, right? If the get lexeme actually consumed the token, you were advancing the token, right? So it creates a situation where, okay, you read something, but you didn't want. So what are you gonna do, right? It's like, this is a funny story. I just had moved to US, right? And I was at Mines as a student again. And I was at the cafeteria for lunch. And they had those plates, right? Pre-served plates, right? With like, and they put like in a table, and you just grab what you want and just move on, right? So they had like chicken, I don't know, with rice, right? So all ready to eat, right? And I was so Brazilians like to eat a lot during lunch. So I look at this plate, and there are like 3 or 4 for you to pick. And I touch the plate, and then I realize, oh, that one is the meat comes with more meat, right? And I decided to go to the other one. The lady that was serving, she got really mad. No, you touch, you get it, right? So I ended up eating the 2 of them. I was happy with that because there you pay like one price and you can repeat and eat as many as you want, right? It was a lot, even for a Brazilian. But that's exactly what happened, right? I did a next char, and if the get char would advance the pointer, right? The phone, right? I didn't want to do it. No, it's too late. You touch, you get it, right? So that's not what we want in this get lexeme and next lexeme, right? We want the get lexeme to give us the ability to touch, look at the plate, right, and put it back. It's okay. No health situation problem. You can touch all the plates, smell, put near your face, and you just grab what you want. And that's what we want in our program. Maybe we don't want it in the real life, right? So please understand the difference between get lexeme and next lexeme, because that will help you in your implementations, okay? Okay, so let's move on. Let's take a look at the code. Activity 7 is not shared, so let me see on GitHub. Maybe the code is on GitHub. It's not, right? So let me get that for you. Apologize for that.
Click it first.
Hi, Austin.
So you're getting your
Have to do this carefully.
Oh, okay. You gotta flex on us like that? Yo, my
Is that a cat? That's a dog.
So your face.
Austin was.
Am I like the only thing?
What's that?
Am I just like the TV?
Yeah.
Oh my gosh. Okay, I'm turning this off.
It's okay.
That's what you get for turning on your camera and trying to be social.
We
Never.
we all watched you do the in-class work too.
Or we can make it mandatory that everyone share their screens.
Whoa. In my previous appointment in Pennsylvania, the campus was dog friendly, So one day I brought my dog to class, Sparky. It's been a lot of fun. But then the chair of the department, he hates dogs, so he wasn't really happy. And he said, no, don't do that anymore. But the students love it. No.
That should be what matters.
So, activity 7 is on GitHub. Can you guys, so just create a new project in IntelliJ, a Scala project idea, and copy the source and in the SRC folder and all the source code so we can start talking about the Lex analyzer, okay? What? Did it again. Can you guys don't look at the code yet? Because on data mine I did this and I did this again here. The code has the solution, right? Syntax analyzer. Yeah, it's all solved. Can you not get it right now?
Definitely.
No problem.
Well, Git.
Because we want to do it together.
I'm here to learn. You're only cheating yourselves, guys.
Yeah. Is that Git cool? Let's see how your screen.
Alright, cool. But you know what? I'm gonna pull it in. What it's saying.
Okay, so I'm going to update again. Just confirming one more time. Okay.
It's a screen.
Just need to change one.
I can see the circle.
I'll give you the code, don't worry. Let's work with the one that is empty.
It's from Sony, so like, you can't see it. I don't know.
I agree.
It's there. It's nice. Freaks. You can see it sometimes.
Okay, so it's, if you could pull the repository again, you should have the methods, but the methods are empty now. So let me share my screen.
Pull again?
Yeah.
Minus 50 uploads. Same program.
So let's start with main, okay? And I guess the first thing we need to do is look at the grammar. Okay, so grammar, as you can see, is right recursive, right? So we have expression can be a term in an expression prime. An expression prime can be addition or subtraction of a term and then expression prime or epsilon. The left recursion was removed, at least for this grammar representation. So, and whenever you are about to write a parser, just make sure you have the grammar, because basically the implementation, you have to follow the grammar. And then you have the syntax analyzer. Let's take a look at the main method, right? So the main method assumes that you should pass a source file through the command line. And after that, it instantiates a syntax analyzer, passing the file name, right? arg0 has the file name. And after that, it calls the parse method from syntax analyzer. The parse method, as I mentioned before, it returns the parse tree. And then we're going to print the parse tree. So before we actually see and evaluate the syntax analyzer, let's take a look at a tree. So a tree class is a very simple implementation of a tree, just very minimal that we need for the syntax analyzer parse tree. The tree is created. This is the, remember this? What is this? Primary or secondary constructor? Primary, right? So this is the primary constructor. The primary constructor expects a label, right? The label is, each node will have a label, right? Usually we're going to use the variable like expression, term, factor. We're going to use those as labels. And for the leaf nodes, the label will be the word, right, that we recognize. So there is this attributes, which is a map. So it's a map that associates a key, a string, to another string. So the label is basically one of the keys. So this tree implementation allows me to create many key value mappings on each node. One of the mappings is the label, but I can add other key mappings to the node if I want to. And then you have the branches, okay? So this is not a binary tree, right? The tree, the node on a parse tree can have 10, depending on the production. You can have many children, right? So the branches are the children. It's an array buffer of trees, because basically this tree is a tree node. Maybe the best name would not be tree, it would be tree node. But basically, it's just showing that the recursive nature of the tree. Each node is actually a tree on itself as we go down, okay? And then you have a way to change the attributes or create other key value association for that tree node. And you can add branch nodes, okay? Just adding to that list of branches. And there is the print. So the print will recursively print the tree from that tree node that you call print, okay? That will give us a view of the tree, and also it will use tabs. Okay, and the tabs we'll use the tabs to show the structure of the tree. If you want to see how a tree looks like, we can actually run this tree class, but you'll probably have to comment out the syntax analyzer. Otherwise, you won't be able to compile. So I comment out the whole code, and I'm just going to run tree. So this tree here is just an example code. It's important for you to understand how to create, because you're going to be creating a parse tree. So you have to be familiar with this tree class. So basically here, we're creating a tree with this node here, A. This is going to be the root node. And then we have AB1, AB2, AB3, and ABC1, ABC2, also with those labels there. So we're going to add AB1, AB2, AB3 as branches of the tree, this tree node here. And then from AB1, we want to add ABC1 and ABC2 as branches. And then we're going to print the tree. So let's look how this tree will be displayed. Okay. So this is how it will look like. That's the best we can do with text interface. But you can see the structure, right? You can see that label A is the root of the tree, and you have beneath this node A, you have nodes AB1, AB2, AB3, and beneath AB1, you have ABC1 and ABC2. Can you guys see this structure? Do you understand that this is a tree? Okay. All right. So let's go to the syntax analyzer again. Comments. So let's take a look at the constructor of the syntax analyzer. So the first thing you have, this is a primary constructor, right? So it's expecting the source file. The first thing it does is to get the iterator of the lexicon analyzer. Remember, the iterators facilitate the communication between the lexicon analyzer and the syntax analyzer. Remember that those has next and next methods, they were implemented in the lexicon analyzer's iterator method. So the iterator in the lexicon analyzer returns an iterator, and this is what the syntax analyzer is doing at the beginning. It's getting the lexicon analyzer iterator, and there is this current lexeme initially is set to null. Okay. So get lexeme, remember get lexeme and next lexeme. So get lexeme returns the current lexeme. Of course, if the current is null, it needs to call next on the iterator to get the actual lexeme, right? Because current is null, you need to ask for another lexeme, okay? If that's the only situation when the get lexeme will ask the iterator for another lexeme, right? When the current is null. If the current is not null, it just returns the current lexeme, okay? So that allows you to control when you want to get another lexeme. Next lexeme, on the other hand, always move forward. So next lexeme, it calls next no matter what. Okay? Understand the difference? Get lexeme will only call for the next lexeme if current is null. If current is not null, it just returns the current value. The first method that's going to be called is parse, right? So parse, we'll call parse expression, right? Because expression is the first variable here. It's the start symbol, right? So to parse this program, you have to parse expression because this program is going to be an expression. The expression is the start symbol. So for each of these variables here, expression, expression prime, term, term prime, all of these variables, until factor, we're not going to do methods for identifier, letter, literal, integer, because they will be all implemented in factor, okay? But all of these will have a specific method, will be parse and the name of the variable. So parse expression starts because we're doing top down. So we start with an expression. So we're going to call parse expression. So expression, parse expression, this is what parse expression is. An expression is defined as a term in an expression prime. So the first to do is telling you to create a parse tree. Create a parse tree with non-terminal value expression. Okay, so let's do that. So how do we create a tree node? Tree, new, tree, and then we pass the label, right? The label is expression. Okay, I guess we need to find, so val tree, new tree. That's it. Good. Now, we need to parse expression means what? Parse a term and then an expression prime, right? So now we need to make a call to parse a term. Each of these methods will return their tree vision, what they're seeing from their point down, right? And they need to return that to whoever called them, right? And that's how things get connected, okay? So parse expression starts, right? And this is the tree for parse expression, right? But then parse expression will call parse term. Parse term will create another tree, like term, right? And we'll start evaluating term, right? But these guys are not connected. This is one tree, this is one tree, right? When parse term is done, parse term needs to return a reference to this tree node so this guy can make the connection. Okay? So returning the tree, each method should return the tree to whoever called them so they would make the connection. Okay, so here, basically, we need to call parse a term, and then we're going to call parse expression prime. And we have to make sure that we connect whatever tree is returned by parse term, we need to make the connection, right? So basically, we need to do tree dots add, then we call parse. Okay. Well, Yeah. So all these methods, so this is a Scala thing. You don't have to explicitly define what the method is returned. It will be inferred when you return, okay? All of these methods now, because I removed the code, Scala thinks that they're returning nothing, right? That's why it's unit. But when we finish each method, because we're gonna have a returning the tree, it will figure out the type of the return type, okay? But if you want, you can explicitly put tree, but you don't have to, okay? Now we got rid of that here, but you don't have to worry about that. Parse an expression prime. Tree, add, and then you make the call to parse expression prime. At the end, you return the tree. That tree, or you can just write tree, okay? You don't have to put return. You just write tree. It's inferred that you're returning it. And you don't need semicolon. Okay? So this tree returned by parse expression, because this method is the first method, right? And represents the start symbol. That tree return is actually the whole tree. It's the whole parse tree. Okay? And that's the tree that is being returned by the parse method. It's whatever parse expression returns. Okay? That's it for this method here. You might be thinking, but this method didn't do anything, right? Just make two calls of other method, but there isn't any non-terminal to be consumed, right? What is an expression? An expression is a term, right? In an expression prime. For the point of view of that function, it's like I can't consume any lexeme or anything. What I have here are two variables, right? It's going to be up to the methods that implement those variables, right? Those productions, to do the consumption of tokens, right? And values, right? For parse expression, the work is done, right? And that's what the recursive descent is all about. As I said, you write a lot because for each production, each variable, you're going to have one method, and those methods may call each other and call themselves too. You guys want to do parse term? It's very similar to parse expression. Why don't you guys do parse term?
The first to do supposed to say create parse tree with non-terminal term or expression.
You're right. Term. Let's copy and paste.
Suppose you're not using constants for all these like factor term.
Like for the labels. Yeah, those are the prime. I don't need. No, that will be included by the. Yeah.
So is there a problem there's not?
No, you pass the string, and this string will be associated to the label, to the key name label. This is not automatic. So you're probably thinking, I'm not doing anything with these methods, right? But don't worry, you will. At some point, you have to do something, right? So create a new tree. Parse a factor. It's almost like these methods are the managers, right? They're telling others what to do, right? But they're not doing anything. Don't forget to return the tree. Now you have some work here. Parse factor. Well, this first to do, it seems you're doing the same thing, right? Tree, new tree. Okay. Now what? Now we need to decide. Am I reading an identifier or a literal or an expression parenthesis? How am I going to decide? Right?
Look at the token.
You need to look at the token. Exactly. So how about we call next lexeme, right? To make sure that we get something to work with, right? So maybe how lexeme get lexeme. Okay, now we need to decide. Lexeme, remember, the lexeme contains the word, right? String and the token, right? What's more important for the syntax analyzer? The token value, right? So let's query the lexeme for the token value and decide what to do, right? For example, if lexeme, right? Dot get token equals to token identifier. Any parentheses. Okay. Well, at this point, you could have done parse identifier, right? But I don't think we have that. Let's just process the identifier here, okay? Because that's the only place where we're going to process an identifier. If it was a more complex grammar where you would see identifier in many different places, then I'll say maybe you should create a parse identifier. But that case here, it's not the case, right? So let's process the identifier. How about we need to create, so we're at this point here, right? the term we didn't connect yet. And then we have factor, right? We are here, right? We created this factor node, right? And we have these pending, right? Because this called this method called this one. So we're right here. Maybe this expression is, I don't know, x, I don't know, plus 8, right? So wouldn't it be nice to have another tree node with the value x, right? And connect it to factor, right? So how about we create a node and use the lexeme value, not the token, right? The label of the lexeme to label this node here. Okay? And let's make the connection. And call this subtree, whatever. Get label. And then you add this subtree as a branch of the tree. Okay. Okay. Trying to remember if I touched the plate or not, right? I call get lexeme, right? If I just return the tree at this point, if some other method called get lexeme again, what will they get? The same guy, right? Same identifier. So don't you agree that this is the time to advance? Right? So we call next lexeme, right? We're just going to be advancing, and whoever called get lexeme will get a new lexeme, right? So I think it's safe to call next lexeme now. And let's evaluate the other possibility here. What's the other possibility now? Literal, right? Maybe we can just copy all that. Careful when copying and pasting. Don't worry about this unit because basically when we're done, we need to return the tree, okay? So replace this by literal. And everything is very similar, right? In fact, can we get these all together? How about we do this? Right? Because everything is the same, right? And let's use the else for the other part here. How we should do opening parentheses, expression, closing parentheses. What do you guys think? So this should be what? Open parentheses. Right? What should I do now? Already consumed the open parentheses. What should I do now? Inside the parentheses, we have potentially we have an expression. Suggestions.
We need to make sure all parse expression.
All parse expression, right? This is where we are. We are at parse factor. It's not the job of the parse factor to understand what an expression is, right? There's a method specifically to parse expression. Why don't we just call that method? all that tree returned by the sparse expression should be added as a branch of that factor, right? Parentheses, and then you have an expression, and then closing parentheses, right? So all these three node trees should be added as beneath the factor node, right? So I would add whatever parse expression, right, returns. And then what? Wait a minute. What about the closing parentheses? So we should check, right, if what's coming next, right? Maybe you should update the lexeme, right? Maybe you should define this as bar and do a tree lexeme, get lexeme. And now you need to check if what you're getting is a closed parenthesis. Okay. Now let's talk about exceptions, right? Errors, syntax errors, right? Because important thing about the syntax analyzer is not just to check that your code is correct. It's also to point you where you made a mistake, right? And, what syntax error you are committing, right? So you need to tell something, like at this point here, at this exact moment, the only thing that after you parse an expression, you had an opening parenthesis, have an expression, right? You should have a closing parenthesis. If you don't have a closing parenthesis, that's a syntax error. And that's what this else is about. You parse an expression after an open parenthesis, but you're not seeing a closing parenthesis token. So you should throw an exception. Right? So you need to throw an exception. You can just say throw new arrow, say syntax. Let's be very simple here, nothing fancy. We're not gonna point the line of the code that had the arrow. We're gonna do something very basic, okay? Just say closing parentheses expected. Something like this. Okay? What about this else here? This else is for, oh, it was an identifier, it wasn't an open parenthesis, it wasn't a literal. That's a problem, right? So we are trying to parse a factor. The only three possibilities are identifier, literal, or an opening parenthesis. If I don't see any of those things, it's a syntax error. You should throw an exception. Error. What would be a good message for this error? Go learn how to code. Identifier Oops. So get used to Python. Use single quote identifier, literal, or opening parentheses expect. That's the best you can do. You can't say exactly what to expect, right? Because parse factor accepts identifier, literal, or an opening parenthesis. Those are the three possibilities. You cannot infer what was in the head of the programmer, right? What was the programmer thinking? That's the best you can do. Okay. All right, nice. Are we done? Oh, you have first term prime. Why don't you guys do that? It's very similar to parse factor. Once you're done, it should work. Now we still have parse expression prime. Because you have the primes, right? Why don't you guys finish these two and we should be good to go. Oh, okay. The term prime and expression prime, they're actually more complex. The reason why is because they are recursive, right? Those two are recursive. So what will be the base case of these recursions? Let's evaluate parse term prime. Okay. Epsilon, you're not going to have a token epsilon, right? So you can't use that. Epsilon is basically there saying you're done, right? For example, if you are parsing a term prime and you don't see multiplication or division, that's your clue to leave, right? So as long as you see multiplication or division, you keep doing those, because you're only going to apply this production here, term prime going to multiplication factor term prime or division factor term prime, if the symbol that you're seeing is a multiplication or division. If you're seeing something else that is not a multiplication, it's not a division, you need to leave. Leave means what? You are applying epsilon. Okay? So now you guys see this the first moment problem that you're seeing the relation, the close relation between the productions and how you interpret that into code, right? So when you see an epsilon in a recursive descent parser, it means that you are done, right? That's how you turn that into code. You leave the recursion, or you return. You don't have to do anything. Okay? So you can start with your tree. Prime. About while true. You guys like while true? let's get the lexeme, right? Get lexeme. So if the token is token multiplication or token division, we're good. We consume the multiplication division or division, right? We consume that token, call parse factor, right? And actually, because I'm doing a loop, I'm not doing recursion, right? I just noticed that. So, do you guys want to do recursion or? Yeah, let's do recursion. So consume this guy. New tree, right? This is what we did here. Okay, the same thing. Although here I created the subtree, I'm doing one step here, but it's the same thing, okay? Oh, no bad. Too intense for my notebook. Okay. Next lexeme, right? And then what? Call parse factor. And then recursively call parse term prime. Okay. Well, if you're not seeing multiplication or division, you should do epsilon, right? Do you want to see epsilon in your parse tree or not? You don't want to see it? Nobody likes epsilon, right? From a programming language or theory of computation perspective, you probably should see it, right? If you guys don't want to see it, do nothing. Okay? Just return the tree. So sad, you guys don't want to see the epsilon. Does that make sense, guys, or is blurred and confusing?
It makes sense, but there's no way to throw exception if there wasn't a multiplication or division.
Yeah, so the error will be caught later, right? Because what's going to happen is probably because you are in a part of the expression where you have multiplication and divisions. But then what's coming next is an addition. So you need to return the parse calls until you reach a place where you can start now branching out for another production that will read the addition or subtraction. This is a great question. You can't throw arrows or exceptions at this point because it might be the case that it's something that another part of the evaluation will catch the arrow, or it will, maybe it's something that makes sense, but in another part of the evaluation. Now let's do parse expression prime. This is very similar. Maybe we can copy and paste. Careful. Careful doing that. So here should be what? Expression prime, right? Here should be addition. Here should be expression prime, right? See? Get that. I was telling my data mining students, you were there, that important skill that all data miners should have, attention to detail. I don't have it. And I'm the instructor. I shouldn't have said that. I'm not gonna lie. Okay, that's it. It should work. We dare to run it? I don't want to run it. There's a mistake. Did it work?
So this is the start of this parenthesis on the string. It's that.
Good. We got something. Okay, so let's take a look at. Are you guys believing that all of that would work? It worked. Okay, let's see. Let's evaluate. We're cheering, but we don't know if it's actually correct. Let's evaluate. So an expression, right, is a term, right? Here's the. Oh, okay. So you have to read this using the grammar, right? So let's look at the grammar. So what was applied here was an expression is a term expression prime. And that's what we're seeing here. What is a term? A term is a factor and a term prime. What is a factor? 52, right? So we got this. Then all of this here is the expression prime. What is an expression prime? Expression prime is an addition term expression prime. You didn't see the epsilon, right? The term prime going to epsilon. It was here, right? Okay. So expression prime is an addition term, and we should see an expression prime. There you go, expression prime. What is a term? Vector, which is the x, right? Term prime. What is a term prime? Multiplication factor 231, right? Term prime. That's the recursion, right? Term prime. Division factor term prime. We have the label. Why? Oh, here we had to do the epsilon because at this point, remember, we are at term prime. We're expecting multiplication or division, but we saw subtraction. So that means what? Epsilon retracts. So those were the recursive calls reaching the base cases, right? So we had the retraction, and we went back to where we were, and we were doing this part here. Expression prime is addition term expression prime. So expression prime is a subtraction term. Term is a factor, that's the 8. And expression prime, you're not seeing the epsilon here, you reach the base case. Okay? Beautiful, huh? Your first parse tree. Let's try other code. Let's see source 2. Source 2 is this one here. You can see identifier, right? If you want to see the label identifier, you can create another node here. We went straight to the value, but if you want to create a sub branching here, you could. And then we had the parentheses, right? Label parentheses, expression. Oh, look at the whole expression within parentheses. Look at that. This is expression. Then we had term 3 minus xyz 3a and expression prime. That went to epsilon. And the closing parentheses. After that, we had multiplication factor 29.
This is source 2?
Huh?
Source 2?
That's source 2. Now let's take a look at source 3. So far, all the source codes were passing the syntax analyze. Look at that. Source 3 now. All good. Let's see if we can find one that gives an error, syntax error.
I got an error on 2. I don't know what I did wrong.
Oh, lexicon analyzer error, unrecognized. Oh, that's actually a lexicon analyzer error. I think there are some syntax analyzer errors. Let's see source 4. Source 4. Oh, that's source 4, right? Source 5. Source 5 should not pass. Should not pass. Look at that. Addition and multiplication. So what the error should be here? Because
Expected literal.
expected identified literal, right, or parentheses. Let's see if that happens. Yes, yes. Source 6. Missing closing parentheses, right? Let's see if that happens. Closing parentheses expected. Source 7. Source 7 is so sad. probably missing identifier, literal, or opening parentheses. And source 8, you have, that should pass. You have the number of parentheses match, that should pass. Let's see, source 8. Whoa, look at that. Insane. Okay, guys, I will share this code with you. You can compare, see what you missed. You're not in data mining, right? So you don't have attention to detail. That's okay, so I'll share this code, and next homework is going to be variation of what we did here. Very simple, so just for you to practice a different grammar, but something small. On Tuesday, we're going to see the bottom up, and I will be tomorrow probably, or Saturday, I don't know. I will be sharing the first programming assignment. You guys have enough to start working on your first programming assignment. And we're going to talk about it on Tuesday, okay? All right, you guys have a great week.
Make some money.
Well,
Size room dogs.
I don't know.
Sweaters too.
How did,
It's gonna start getting cold. I want sweaters.
I'm sure it's not gonna have a typo. It's that